Today we're going to finish our section on diodes, and there are a few, I guess, different topics to talk about. The first I want to talk about is load lines. So we know that for our diode model, the answer we get is an approximation. And given this, exponential curve behavior of the diode, we would like to know if there is a better way of getting a more precise answer. So load lines is one possible way to do this. So let's take an example. Let's say we have a very simple circuit with a DC source and a resistor and a diode connected to this circuit. So let's say this is 5 volts and this is 1 kilo ohm. And let's imagine that we have connected, this is our supply circuit, and we have connected the diode as a load to this circuit. So just thinking about this supply circuit, we can graph all of the different possibilities of voltages and currents that this circuit can supply. And it looks like this. So we know at a current of 0, no current flowing through the resistor, the voltage across these 2 points is going to be 5 volts. We know if this is shorted, if we just connect a wire there, there's going to be no voltage and 5 milliamps of current, right? 5 volts across 1 kilo ohm. At voltages and currents in between, it turns out the connection between these is a straight line. You can prove this is true with a little bit of math, but this is the load line, meaning that these are all the possible solutions to the load that this circuit could have. So for any load connected here on the right, different values of the resistor or different other components, that is going to be some point along this line. In order to find out the behavior of this diode, we just need to superimpose the diode curve over this graph. So if we know the form of the diode curve in terms of an equation, we could draw it we could figure out exactly what it looks like, but we'll just draw kind of a cartoon. So this is our diode current versus voltage graph. And so these are all the different possible combinations of current and voltage that the diode could have. And finally, the one spot that works for both of these things is is what this circuit is going to do. This is called the operating point. So in this way, this obviously, if we're only drawing the curves, this only gives us a graphical solution. But if we know the numerical form of these, we could, have a computer solve for the intersection of those or something like that. And you can do this with other more complicated components as long as you know what this curve looks like. You can figure that out. So one thing I want to say about the load line itself for this circuit. Our load line is linear. Like I said, you can show that with the equations. But in fact, for any complicated combination of resistors and voltage sources or current sources, our load line is going to be linear because any circuit can be reduced, any circuit made of resistors and voltage sources can be reduced to a single voltage source and a single resistor. That is, our load line is always going to be linear for circuits, for supply circuits like this because of Thevenin equivalence. And so that's one useful piece of information. The load line is always linear for linear circuits. Maybe we should say linear supply circuits because the diode's not linear, right? But yeah, all right, great. That is load lines. We won't have to use this. I just think you guys should have seen it before since it comes up in spec sheets for pieces of equipment and things like that. So it's good to have at least heard of load lines. All right, next I want to talk about rectifiers. So in electronics language, a rectifier means the same thing as a diode. It is something that lets current through one way and not the other way. However, rectifiers are generally the term used in power supplies when that component is handling a large voltage or a large current in an attempt to to turn one sort of power supply into another sort of power supply. And in fact, what we're going to talk about is turning an AC voltage source into a DC voltage source here, very, very generally. So in other words, rectifiers are kind of synonymous with diodes, but it means we're using these to generate a power supply, not manipulate electronic signals. So different rectifier circuits there are two popular rectifier circuits. The first that we'll talk about is the half-wave rectifier. And that's going to look like this. So let's say we have some input voltage that goes into a circuit that looks like this. And we have an output voltage over here. So let's say our input signal is a sine wave, and it is between, we'll say V naught, or V, I guess I called it, let's call it V naught. So that's plus V, this is plus V naught, this is minus V naught. V naught is the amplitude of this voltage. We don't care about what the frequency is, it's not going to make a difference. So our output voltage over here, if we treat this as an ideal diode, so that is, there is no drop in the forward direction, we're going to end up with the following graph. We're going to end up with something like this, where this is 0 volts, and this is exactly following the top half of each of these sine waves and is going right up to V naught. So in other words, for the top half, it is exactly identical to the top half of this, and the bottom half of this is exactly 0. For a real diode, our graph isn't going to be exactly this shape, and that's because we're going to get a small drop in the forward direction, right? If this is a silicon diode, we're going to get like a 0.7 volt drop. So we're going to end up with something that's the same shape, but our peaks are just a little lower. These are still 0, but here, instead of V naught, we're going to have like V naught minus whatever the diode drop is. So if this, like for example, if this was plus and minus 5 volts, ideally this would be going between 0 and 5 volts, but for a silicon diode, it's only going to be going between 0 and 4.3 volts, right? Because we have this forward drop when we have current flowing that way. All right, so this is the half-wave rectifier. So this may not seem useful, but look at what we have done. This signal has its average voltage at 0, right? This is symmetric above and below 0, so the average of this signal is at 0. Our ideal rectifier, its average is definitely no longer 0, right? This is above 0 or 0. There's no negative. So our average, it turns out, is some value here for the. I guess I'll write it down here just because there's more room. So the ideal rectifier for a sine wave, the DC component of the voltage, which is another way of saying the average voltage, that is equal to V naught, the maximum, times 0.318, which someone may notice is 1 over pi. And that has to do with how we integrate this, integrate half of the sine wave over this period. So we put in a 5 volt sine wave. We put in a sine wave between plus and minus 5 volts. We get something between 0 and 5 volts that is going to have an average voltage of 5 times 0.3 is about 1.5 volts. So an average voltage of 1.5 volts. So this is the half-wave rectifier. All right. Now let's look at the full-wave rectifier. Similar in spirit, but a more complicated circuit. So here, our input voltage is not going to be relative to ground. Our input voltage is going to be between these two wires. And we're going to construct what's called a bridge from our diodes. So here's our diode bridge, and between these 2 points is our output voltage. So this is kind of tough to draw on the board, but hopefully you get some idea of how this is constructed. So this is a full wave rectifier. This is not the only full wave rectifier. If you're using a transformer, which we'll learn about later, you can do it with only 2 diodes. But this is a full wave rectifier with 4 diodes configured as a diode bridge. Okay, so we can go through the circuit analysis. I'm just going to skip to the answer. So if we put in the same sine wave as before as the input, so this is between plus and minus V0, our output, our ideal output, looks like this. It is like the absolute value of our input signal. It goes up to V0 every time. And the average of this is significantly higher than the other one. It is, so the average voltage, which is also the DC voltage, the DC component, this is equal to 0.636 times V0. So that is, the average is twice as high as the half-wave rectifier, which shouldn't be surprising because we have twice as many of those. We don't have these big gaps. So this is the ideal case. The real one I'm going to draw in green just so you guys can see it. So the real one is also going to have a diode drop. So in other words, our voltage is not going to come up to the peak. It's going to be, somewhat below the peak for each of these. And that's because we get the forward drop for these diodes. All right, so the full wave rectifier and the half wave rectifier are very useful in building power supplies. Well, we will learn about this later, but I will give you the cartoon version now, which is that if we take this signal, this signal that looks like this, and we put this through a low-pass filter, all of this oscillation, the low-pass filter can remove those frequencies and leave us with only the very low frequencies. In this case, the very low frequency is, the lowest frequency, f equals 0, is this average value. So if we send it out of the low-pass filter, we can end up with a voltage output that looks like this, that is constant in time and approximately equal to this DC voltage. Now, of course, there are some issues with constructing a filter circuit to do this, and even further issues come up when you put a load on this and actually have current coming out of the low pass filter. But at least conceptually, this is how you can make a DC voltage source from a oscillating input. And this, at least conceptually, is how many DC power supplies that plug into the wall work, because they have to convert this AC signal from the wall to a DC voltage.